Andrey has graduated from Moscow Institute of Physics and Technology in 2005. Pretty much every Russian you know has came from the same college. There are some exceptions, but almost all of us came from the same university, and most of us came from even from the same department. We have 9 departments, all of them are physics, different types of physics at the university. So in 2006, Andrey joined our group, and he's been working on CDF. He started here, and then he spent a significant fraction of his time at Fermilab. He was working on Higgs searches at the Tevatron with tau leptons. And in 2011, Andrey has graduated and got a job at the University of Chicago with Henry Frisch, who was, this is a small world, Henry Frisch was postdoctoral advisor of Dave Tobak. Graduate student? Yeah, graduate advisor of Dave Tobak. And so since then, Andrey has been working on this new technology with aimed at really very high resolution detectors, and so he will talk about potential implications of these fast timing detectors for neutrino-less double beta decays. But for us, the people at the LHC, there is more and more talks at the LHC about how to deal with this incredibly high pile-up environment, and one of the solutions that people are talking about is trying to utilize high precision timing detectors, because then you will know if a particular particle came from this interaction or another interaction. That's another way to deal with those high luminosity, high intensity regimes. So there is probably much more to it than just neutrino-less double beta decay, and Andrey, I'm sure, will say at least a few words about other applications for that. So with that said, so Andrey, please.
Thank you very much for introduction. It's a really great feeling to be back to College Station. Last time I was in this room, it was my defense. And now I'm happy to present you with work I've been doing for the last 2 years. And my title is almost an outline. So I will talk about the development of large area picosecond photodetectors. And then I will spend half of my talk showing how it can be used in a very new way for searches for neutrino-less double beta decay. So this is a more detailed outline of my talk. So I'll start from motivation, why large area picosecond photodetectors are a hot topic. I'll go over the design concept, and then I will go over all individual components. There are several of them, and I will shed light on key of the components of LABPD. Then I will switch to neutrino-less double beta decay, explain why it is interesting and what it is. And the idea we were developing recently is how to use Cherenkov light on top of huge amount of scintillation light using fast timing detectors, and how this can be used in searches for neutrino-less double beta decay. This is key institution of our large area picosecond or LABPD collaboration. I'm really glad to represent all these people from national labs, universities, and industry. This is a truly multidisciplinary group of people. We have chemists, high-energy physicists, material scientists, engineers, and we even work in the Space Science Laboratory at Berkeley. So the work I will be showing here is the contribution from every person from this institution working on our project. So the project has been started by people doing high-energy physics. For many years, people were reconstructing jets at collider experiments, and some of them got really sick of it. So they wanted to reconstruct every single particle we see in a hadron jet. So if you can do that, then many searches can get, you can follow the flavor of a jet, and for example, you can reconstruct 4 momentum instead of 3 momentum. The problem here is that we are talking about very dense and fast-moving particles. But if you precisely measure the timing, then you know so that photons arrive first, they followed by more heavier stuff like pions, kaons, protons, and the time differences are here of the order of a few picoseconds, depending on the energy and on the time of flight baseline. Most modern and up-to-date system has time resolution of the order of 100 picosecond, and the goal of LAPPD collaboration is to bring this down to 1 picosecond. Let me show you some more examples on how precise timing can be used at collider experiments. So with high luminosity runs at LHC, events will be looking even more ugly or pretty, it depends on your perception. But there will be many, many vertices. And one thing to do is, for example, for Higgs searches, you need to know where the photon was originated from. You need to tie the photon with the correct vertex. And fast timing can really help here. Or I have an example of these two processes, which are crucial to measure with high precision at LHC. And one of them is vector boson fusion and WW scattering. In this process, you often have two forward-going jets. And forward region is very hard to instrument, but if you can have timing devices in the forward region, then you can tag those forward-going jets using timing information. You can tag all the particles to the correct vertex. So this is how the project gets started. Now let me tell you how we got funded. So in the time when Duzel was around, this is a deep underground facility, and NSF has a very strong support for this program. Howard Nicholson from DOE at that time was pushing forward the idea of building optical TPC. Optical TPC is mostly like a normal TPC with the gas where you're drifting electrons, but instead of drifting electrons, you're drifting the light which originates from charged particles traveling in a media with a speed higher than the speed of light in that media, so-called Cherenkov light. If you can very precisely sample wavefront from this light, then you can find when the photon hits the detector and track it back and project the point where the photon was emitted. It's not as simple as I'm telling it, because there are no preferred direction in optical TPC. When in conventional TPC, you always have a preferred direction. So in this case, electrons go into very different directions, but the light is emitted at a certain angle. And if you use statistical arguments by tracking not the single photons, but ensemble of photons and tagging the time of those photons, then you can reconstruct most probable trajectory of the charged particle. Some work has been done by Matt Wetstein from University of Chicago. He demonstrated that for time resolution of the order of 100 picosecond, and for pions which are of the order of 1.5 GeV in this particular case, you can really separate two tracks. And this looks very, very attractive for Photo-Detectors neutrino detectors. Another application for fast timing is rare kaon decays. In a rare kaon,
tracks, I'm sorry. So it was pi zero.
So pi zero goes to two gammas. They convert to electrons, and those electrons goes. They are very boosted, and those two.
So basically, you're taking photons. In this,
you're taking photons. In fact, there are two electrons, but they boosted, and typically we resolve only photon tracks. But this separates pi zeros from electron background, which would be just one track. And this is the power is that you can discriminate two tracks versus one track. Right, on rare kaon decays, the major background for them is accidental gammas when they do pi zero reconstruction. If you know where and when particle hits the detector, again, you can reconstruct the vertex and significantly reduce combinatorial background. In Chicago, we have easy access to photo people who are doing rare kaon decays, and they would love to have a pre-converter in front of their detector, which has time resolution for photons of the order of 1 picosecond. So this is set standards for us how well we should do it. Another application is medical imaging. In medical imaging, for example, in positron emission tomography, what you have two gammas, two electrons from gamma conversion going to the opposite directions, and you measure the signal on the opposite sides, and by the time difference you construct where the vertex of those two photons. The worse time resolution you have, the longer this uncertainty, this like space location. You have worse resolution when on the position if your time resolution is not good enough, because there is uncertainty where the photon would be originating from. So a group of us shown that for time resolution with the order of 50 picosecond, you can significantly improve the spatial resolution of this imaging, and that would reduce the dose which patients get during the positron emission tomography. Right. Now let me go into more details what the LADPD project is. So we like transformational changes more than incremental changes. So we'd like to change the way how usual photomultipliers look like. Most limitation in time resolution in photomultipliers comes out of the fact that this is very long tube, and there is long drift time for electrons which are getting amplified in this diamond structure. And the longer this distance, the more uncertainty we have. So we'd like to make detectors that are flat, basically get rid of this vertical direction. And we'd like to do it in a way that we can cover large areas with fast timing and do it in an inexpensive way. And the joke we have is that out of these three, you should pick two, and we can do it right now. So pick any two out of these three. The beauty of this design is that it's modular design, and we envision building a super modules where you can tile these devices next to each other, where they would share the delay line for signal processing, and this would significantly reduce the number of electronics you have to put in. On the next slide, I have a little bit more on the supermodel. So the supermodel is what we see as a combination of these little tiles, and little tiles are 20 by 20 centimeters long. And what we are developing right now in Chicago is a supermodel which has a structure of 3 by 4 tiles. This covers almost half a meter square. This is simple glass body detector, and most important thing, the tiles share single delay line of the anode. So you really save a lot on the electronics. And we do have electronics which is fully integrated, and I will talk a little bit more about the details how the electronics work. So the principle of operation of our detector is shown on this slide. This is a design drawing from 2010 of the detector, and this is a photo of actual parts from last year. There are two microchannel plates that are separated by grid spacers. They're all made of glass, and they put into the glass envelope, which consists of glass sidewall and the anode. And the sidewall and anode are treated, so it produces hermetic packaging on the bottom. Then you put microchannel plates and grid spacers inside, and you cover it from the top with a window which has photocathode. Then you have incoming photon. It produces photoelectron on the photocathode. There is a high voltage potential across the whole vertical stack, and the microchannel plates act as an amplifier. So they're like a gain stations in the diamond structure of photomultipliers. So you amplify the signal, we use two plates to improve the amplification factor, and then we collect the avalanche of electrons at the anode, and we have readout to read the signal from the anode. What we like about this design is that it's cheap, widely available float glass. Basically 99% of the detector consists of glass. Anode is very cheap. It's a silver strip screened on the glass This is a similar technology which is used for production of T-shirts. So the way people do pictures on a T-shirt is basically the same as used in our iron structure. It is flat panel and it's a low pin design. So we have single high voltage cable connected at the top and DC current going through the whole vertical stack, and the voltage distribution is controlled by resistance of microchannel plates and grid spacing. So there is always a little current going through, and the resistances of the internal components are controlled by so-called atomic layer deposition process, which we use to functionalize the plates. These resistances can be dialed to our specification. So basically, yeah.
How does it? What is the RPC time resolution? That's a few picosecond.
RPC, as far as I know, the records are in the range of 50 picoseconds, and the typical numbers are 100, 150 picoseconds.
Okay. So your time is...
Yeah, let me get into the timing. So I'll
now
compare.
here, going back to the PMT, you're probably not trying to replace PMT when it comes to low energy, right? Because single photon counting would still be inefficient using the...
Well, let me get to single photon resolution. So we'll see. What it is? What I wanted to add here is that it's a modular design, and the bandwidth of our detector is very high, and the impedance is 50 ohms, so it's ready to be plugged into the electronics. And we have collaborative effort with Berkeley Space Science Lab, which do this in ceramic packaging. So they don't use glass as a body, they use ceramic. Here are the key components of our project: microchannel plates, electronics and integration, hermetic packaging, and photocathode. I will briefly mention photocathodes. I will ignore hermetic packaging because it's so detailed, and I spent a year and a half working on that, so I would occupy the whole seminar time if I would start from hermetic packaging. So let me go into microchannel plates. Principle of operation of microchannel plates is very simple. Microchannel plates are the thin glass, sort of 1 millimeter, with multiple pores which are between 10 and 40 microns. If you apply high voltage across the pore, then electron hitting the wall would get amplified because the inner structure of normal microchannel plates is covered with material which has high secondary electron emission yield. And at the end of the pore, you get an avalanche of electrons. And this is very old technology. It's almost 50, 60 years old. The problem is that it's very, very expensive. It has been widely used in night vision devices and military industry, but the way they produce these microchannel plates is very expensive. So what we do, we buy cheap glass substrates from Income Incorporated company. They found a way very nicely manufacture microchannel plates from glass. And here are a few pictures of microchannel plates of large size. 20 by 20 centimeters, all from borosilicate glass. This particular one has 1.2 millimeter thickness, pore size 20 micron, and the open area of these microchannel plates is between 65 to 83%, depending on the manufacturing process. So this is all very great. It's a perfectly made microchannel plate, except that it's completely useless because there is no secondary electron emission layer in the ordinary glass. If you hit glass with electron, it will not produce secondary electrons. So the way around this problem is atomic layer deposition. I know zero chemistry, but I'll try to explain how the atomic layer deposition works. So basically, you put a single atomic layer of material onto a glass, and this material has a property you like. For example, what we do, we take porous glass, we put resistive coating, so we control high voltage, and we put emissive coating to get the gain out of the detector. And we also have electrodes to make electrical contact. So the way atomic layer deposition works is that you create a material which sticks to the surface but does not stick to itself. And if you wait long enough, then long enough is seconds, but for chemical processing it's quite a lot. And in this case, material would stick to the surface, but if you continue to wait, it would not stick to itself. Then you take similar molecules with similar chemical properties, but modify it just a little bit. So it does stick to the layer which you already deposited, but will not stick to itself. And you repeat this procedure several times. If you do it multiple iterations, you know that every time you complete the cycle, you have one atomic layer. And this way you very precisely control the thickness of the layer you are depositing. And the chemistry can be dialed. These two guys are great. The magicians in our project. They produce many plates which are standard industry size. And just recently, when I joined the project, we started working with 8 by 8 inch plates. And they use this for quick tests of chemistry, and this is our real operational device.
Was that your photocathode layer that you were showing?
No, this is MgO layer. The secondary electron emission is magnesium or aluminum oxide, and it has this color.
And that has to be done to ALD?
Yes, this is done through ALD process.
Can it be done? So you said aluminum and magnesium?
Magnesium oxide or aluminum oxide.
Can they be done through sputtering?
No, because of high aspect ratio, the sputtering will not penetrate through these pores. So we only use sputtering for we use sputtering only for electrodes because we need electrodes only on the surface and we don't want it to go inside. Right, so quick results from our colleagues from Berkeley. This is a typical pulse shaped from 30mm microchannel plate. The gains for two plates are the order of 10 to the 7th. And this is a typical pulse height distribution. What I'd like to draw your attention to is to this plot. This is extracted charge. So you have put plate under the operation and you draw the charge from it. And you look how the gain changes. And what is shown in these colored lines is the performance of ordinary microchannel plates which industry manufactures. So after a while, after you extract half a coulomb, they degrade and the gain becomes low. This is a test of ALD MCPs fabricated at Argon, and the live test shows that after even 7 coulomb, there is no significant degradation in the gain. With uniformity on 8-inch plate, we have big success. This is the uniformity of 8 by 8-inch plates. This is a slice how uniform it is. And if you don't think it's uniform enough, let me show you the next slide. It shows the evolution of the project. So we started from gain non-uniformities, which looked like this in at the end of 2011. And by the end of last year, we ended up with plates which perform beautifully, and we really believe that we can put them into a seal tube and produce first seal device.
So what cause of the
non-uniformities basically is you have the structure of the MCP plates. These pores are not quite uniform, and there's different geometry here. For example, if you hit the joints, it won't be the same gain as if you hit the center. And also the ALD process, so it still has to be improved. There are a lot of room for improvements. But most of these improvements came from better substrates and from better atomic layer deposition process. So photocathode, just a few words. I'm not a world expert on photocathodes, but our project requires photocathode. And so far it has been sort of a black magic. People mix different materials and they get a photocathode. And we tried that. At Argon, we built a facility where you can test production of photocathode of large size. So this is 7-inch window, and this is a uniformity of the photocathode on 7-inch window. And the typical quantum efficiency we got was of the order of 15%. So we didn't quite hit 20% as promised, but it was very close. And our Berkeley colleagues, they do very well. They produce photocathode with quantum efficiency higher than 20%. And important thing with Berkeley guys that they do it in a chamber which is suited for production of the whole tube. So we at Argon, we could only deposit photocathode in a place where you cannot put any detector. It was pure R&D research how to make photocathode. What these guys doing, they put it in the chamber where they can control the whole process from abrasing the ceramic body, putting microchannel plates inside, and closing it with the photocathode. So that's it on the photocathode. And let me go to our electronics. So as I said, we have anode. The design for anode was to make it cheap, 50 ohm impedance, and bandwidth with this range, depending on the length. As I said, we have a modular design so it can be combined. And one of the things we have checked is how the bandwidth depends on the length of the anode. So at 90 centimeter anode, when we combine 4 tiles in a row, we get 400 megahertz, which is pretty cool, I think. And for impedance, the measurements are shown here, and the results have been published in a new paper. It has all the details about anode. The way we read signal from the anode is we use our custom-made electronics. Most of work has been done by our graduate student Eric Oberla. What he did, he designed an ASIC chip with 17 gigasample sampling rate, 1.5 gigahertz bandwidth. It was exactly to match the impedance of our anode if you use just one dial, which is 1.5. And this is just a cool picture of the same signal read out by the scope and by this what we call scope on the chip. And so our next step was to implement all these components, microchannel plates, anode, and electronics into a single package and test it. So we have the very broad program at Argonne. We test microchannel plates, which are 33 millimeter size to give quick feedback to chemistry. We have giant chamber where we can put the whole stack inside and test it without worrying, making good hermetic packaging on the glass envelope itself. And we built a real system with one active component and 3 more active anodes, which we use to propagate the signal, and we read out the signal with our custom-made electronics. And before I show you the results of these tests, let me tell you that Argonne got very excited about this, and we got an invitation to publish our work in a journal which is called Review of Scientific Instruments. We made the cover, and this is a group of people who are primarily responsible for these results. So I will skip 33 millimeter tests and we'll go directly to 8-inch. So this is our chamber. We use a very fast femtosecond laser to produce pulses. We need laser for several reasons. One is that we don't have to worry about what the jitter of our photon beam which produces signal. So we want to exclude that from consideration. And the other reason that we use aluminum for the cathode, and you need very high powerful laser in order to produce some photons with very low quantum efficiency for the cathode. So aluminum quantum efficiency is about 10 to the minus 5, and we have laser beam with millions of photons. This way we always get some photons from our photocathode. So we first observed gains of the order of 10 to the 7th. It was very comparable to our 33 millimeter tests. And next thing we tried is to test timing characteristics. We started our test by reading signal from both ends on the anode and shooting the laser into the middle of the anode. And by time difference in arrival of the signal left and right, we could tell where the beam is located. This is a photo of our setup. So we put the stack with microchannel plates and grid spacers inside, and we seal the chamber, and we have this mirror to reflect the laser beam coming through this window over here. And this plot shows the linearity of the response. So you move the laser beam along the strip line, and you notice that the time difference of signal arrival to the left and to the right changes. And it changes linearly. This way you can measure the propagation speed along the anode. And for our first test, we noticed that we are getting 15 picosecond differential time resolution. We call it differential because it differentiates between left and right side. When we look closely into our data, we found out that if we select pulses with very high amplitude, we are doing much better than 15 picosecond. So this plot shows the noise to signal ratio. So this is very high amplitude signals with low noise, and this end is high noise, low amplitude. And this is a differential time resolution as a function of this noise of the signal. So we are getting down to 5 picosecond with very high amplitude pulses. They are not single photoelectrons. They're about 2 or 3 photoelectrons according to our calibration. And this differential time resolution corresponds to about 0.5 millimeter spatial resolution. What about absolute time of flight?
Yes, right.
Yeah.
So you have a blue curve simulation that looks in about 2 point you simulate.
Yeah, let me tell you what it is. So for simple simulation, you really need just 1 point. There is a linear dependence on your noise versus your signal. And I should have said it, that the reason we deviate from the simple simulation is because our laser has limited size, so it's not exactly a point. And because you never know which photo the pulse produces.
So that's consistent.
So the difference here is very much consistent with beam size. This is 2 picosecond difference, and the beam size is about 200 microns, so 0.2 millimeters. So this is very much consistent with beam size of our laser. All right, absolute time of flight resolution is when we tag the laser beam and we compare the absolute time which we measure at the microchannel plate. So with 8-inch setup in the chamber, we got about 50 picosecond, and this is single photoelectron response. So this we calibrated to the extent that we know that we are dealing with one single photoelectron coming out of our photocathode. With small system, we get down to 17 picoseconds. This is our best result on time of flight resolution so far. We got pretty excited about it, and we decided to move ahead and build a complete detector system. So we started from building a single module. So from this moment, we don't use our 18 chamber where we create vacuum. So we seal it, but the way we seal it is ordinary O-ring, and we use quartz window with aluminum photocathode. We compress it, start pumping, and this way we create vacuum. And this vacuum would stay as long as you continuously pump. So our system here is attached to a turbo pump, which gets us to the vacuum absorber of 10 to the minus 7. We have the laser station on the table, which we can move. We can do very different tests, scan across the strip lines, scan along the strip lines, measure time resolution, position resolution. And the reason we started from this segment here is because we keep in mind our goal of building a supermodel of 3x4 tiles. And this is one step forward from this setup to supermodel. And these photos show how the electronics get connected. So we connect our ASIC chips directly onto the strip lines. So the signal coming out of the strip lines go into the analog ASIC, and this ASIC talks to the FPGA, and from FPGA you get the full waveform from the analog. This plot show how we reconstruct position using our detector. So for position in the direction perpendicular to the strip lines, we use signal centroiding. This plot here shows the signal for, I guess, maybe 10 different events, the distribution of the signal along the strip line. So the central strip here gets most of the signal, and because of the crosstalks, the neighboring strips got some signal as well. By doing centroiding, we managed to get down to 0.7 millimeter spatial resolution in the direction perpendicular to the strip lines. The direction, the spatial resolution along the strip lines is measured again by the time difference. So we measure signals arriving to the left and signals arriving to the right. Again, you can check the linearity. So if you move the laser beam to the left or to the right, the distance between these two pulses should move. And this is the linearity plot showing, again, about 2/3 of speed of light. I use 2/3 because it makes easier conversion factor from delta t to delta x. So these are all approximations. But this is very much consistent with what we get on our 8-inch setup. And the differential time resolution here is about 18 picosecond, and it corresponds to 1.8 millimeter. And just a reminder that for 20 centimeter anode, we got 0.5 millimeters. And of course, the most interesting test is what is the time of flight resolution on this long structure. This is 90 centimeter long anode. It acts as a giant antenna, so it picks up every possible noise in your lab. And we have a very powerful laser which intrinsically produces a lot of noise. And this noise is very much correlated with the timing when photon pulses are coming. So we are reconstructing our pulses that are sitting on a very large noise coming from the laser. And even with this, using oscilloscope readout, you get down to 35 picosecond time resolution, and with PSEC for our electronics, we get to 80 picosecond. And for this particular run, we did not calibrate electronics. It was just ran out of the box. So Eric came to our lab, installed electronics, we did a run, and we got this resolution. So we were pretty satisfied at that moment. And we recently, our paper was accepted in A, describing all these results. And we all was pretty much impressed with this time resolution on such a long anode, because the anode doesn't have to be that long. This is for this particular application where you're building a supermodel. If you look at single tile, you will do much better. So where do we go from here? The goal for this project is to make them commercially available. So you can go to a vendor and buy it, make the specs, and use it in your physics research. Universities and labs will do optimization guidance, and we will continue to develop LD process for fabrication of MCPs. Chicago will continue to work on electronics and photocathode. But the major goal was to make them commercially available. DOE has been very supportive to our project, and just recently, almost 9 months ago, they awarded phase 1 of small tech transfer to Incoming Corporation, and they are in the process of making first sealed tube. So the phase 1 is to make one tube, demonstrate that they have all the production line to make one tile, and the phase 2, which is several millions, will be used to make them, produce them several, get them into the field, and so people can start testing them. So on applications, we hope to bring them into the field very soon, and we invite people to think what fast timing and large area coverage can do for their experiments. Here are some examples of people who are very serious about it and submitting proposal to Income and making purchase orders, not quite, but very close to making a purchase order from Income. And let me now switch to what I think is very attractive in these detectors. So LAPPDs are digital photon counters. They can measure position and time for each individual photon. And photons can be tested for several hypotheses, especially if you have ensemble of them. You can test for vertex, for propagation history, scattered light versus direct light, and for production mechanism. This thing here I found particularly attractive because if you can separate Chenkov and scintillation light, then you can move forward with Neutrino-less double beta decay searches, and not only look at the energy, but also at the topology of the events. And let me maybe switch to this topic through the rest of my talk. So what is Neutrino-less double beta decay? This is a process when a nucleus changes its charge from Z to Z plus 2. It increases it by 2 units, and it emits 2 electrons. This has to be compared with normal beta decay. In normal beta decay, charge changes by 1 electron, and anti-neutrino get emitted. If you look at each half of this plot here, on left and right, then each of them looks like a normal beta decay. but neutrino emitted at this vertex get absorbed at this vertex, and vice versa. So this is very interesting, and interesting for the reason being it's only possible when neutrino is its own antiparticle. This is so-called Majorana neutrino. So Majorana particle is a particle which is its own antiparticle, and many theoretical work has been done on neutrino mass origination, and many theories suggest that this is a preferable scenario for explaining the mass of the neutrino. The signature for this process is pretty simple. There will be two electrons. It's very well-defined energy, because the energy is the difference of nucleus in this state and into this state. And the kinetic energy of two electrons will be as a delta function, because the energy of this process is very well-defined. And typical energy is about 240. So what are the challenges? One of the challenges is that it is very rare process. And when you have a rare process, you have two options. One option is to build a giant detector, and another option is just to wait very long. But in this particular case, when you have half-time observer of 10 to the 25 years, you would have to wait very, very long time. So the only way around here is to build giant detectors. The decay rate depends on matrix element and so-called effective Majorana mass, and everything else which you don't understand, you put into the phase factor G. This plot shows how the effective Majorana mass observed in neutrino-less double beta decay depends on the lightest mass of the neutrino. And as you can see, all currently running experiments are over here. They are around exosensitivity, and they are far away from sort of interesting region of inverted hierarchy. Theory, some of future experiments plan to get into the inverted hierarchy region, but as far as I know, there are no real plan to get to the bottom of this plot, where you need 1 ton of the detector mass. And to really nail down the question, you need at least 10 ton of material which can undergo neutrino-less double beta decay. So what we are thinking is that we should look at this problem quite differently. The challenge is very tough backgrounds. And in order to discriminate from backgrounds, you have to look at the topology of the events. So what most experiments do, for them, most difficult background is 2 neutrino decay. 2 neutrino decay is a process when there are 2 nucleus undergoing normal beta decay at the same time in the same nucleus. And there are 2 neutrinos emitted. And as a result, the spectrum looks very much like in the case of normal beta decay. So if you look at the spectrum of 2 electrons, there is always a possibility that some fraction of energy was carried away by neutrinos, and the spectrum is going like this. When you have no neutrinos in the interaction and you measure total energy of 2 electrons, the energy spectrum is basically a delta function. This plot is an optimistic view of this, because the size of this spike here is order of magnitude smaller than the tail, because the probability of neutrino-less double beta decay is several order of magnitude smaller than the probability of 2 neutrino double beta decay. And this is just an example how different experiments deal with these backgrounds. Number of backgrounds and variety of backgrounds is great. You have everything you can possibly imagine. And there are different techniques how to reduce those backgrounds, but everything comes down to a point where you have energy spectrum, you define your signal region. In the case of EXO experiment, it's around this magnitude, 2.4 MeV, and you look for an excess of the events here. This is utilizing energy conservation. But there is also momentum conservation. And momentum conservation tells you that neutrinos coming out of double beta decay should have back-to-back topology most of the time. So this is a simulation of double beta decay in a cadmium in a sphere of radius 6.5 meters. And what are these green lines are the Cherenkov line. So electrons produced in the double beta decay are produced above Cherenkov threshold. So what we propose to do is to use scintillation light to measure energy. You can't get away without energy measurements. You have to measure where the events sit on your spectrum. But then use topology of the events and reconstruct this back-to-back topology using Cherenkov line. Electrons are typically in the range of 1 MeV, and this plot here shows the spectrum for media with index of refraction of 1.4. Most of the electrons are above Cherenkov threshold. But of course, there is a huge amount of scintillation light. And the key thing here is to separate Cherenkov light and scintillation light. In order to understand how to do it, we started.
What do you mean by scintillation light?
Well, many experiments like CAMLAB, they dope their scintillators with material which can undergo double beta decay. So you have source material like xenon, which emits 2 electrons, and then it's surrounded by scintillator, liquid scintillators. And in this scintillator, when the charged particle goes through, it emits light. This light is isotropic, and it's
Oh, okay. So this is light from the electrons
electron,
moving through the scintillator,
yeah.
as opposed to the Cherenkov light that's coming from the speed. Is that
right. Yes.
Okay.
Yeah. So the big difference between Cherenkov light and scintillation light is that scintillation happens in the media, and it is delayed with respect to Cherenkov, which is prompt. Cherenkov light happening prompt as particle goes. It's like a sound wave, and the scintillation has a little bit of delay before you excite all the atoms in the media, and they emit light back. So we'd like to use these differences in production mechanism of scintillation light and Cherenkov light. And to start this, we simulated 5 MeV electrons in CAMLAB scintillator. 5 MeV is not quite the energy range for neutrino-less double beta decay, but when you do something like this, you don't want to get scared by the fact that nothing works. So we started from something which we knew would work, and 5 MeV is much lower than anything else which people tried before. So this spectrum, in terms of wavelengths, looked as follows. Huge amount of scintillation light and a little bit of Cherenkov light. And Cherenkov light for such low energy electron sits in a red area. I use blue line for the plot, but in fact it has higher wavelengths, meaning that it's more red. And this is a little bit unusual for most experiments using Cherenkov light. In most cases, people think of Cherenkov light as a blue light, but this is because the energies are much higher. For low energy particles and for different type of scintillators, it's more on the red side. So this is the difference in the wavelengths. What is mostly important is that the time structure is very different. This is the standard time resolution of CAMLAB phototubes, and you can see that there is a little bit of difference between Cherenkov light in black and scintillation light in red, but basically you can't tell the difference. They're happening at about the same time. We tried to use 100 picosecond, which we think is reasonable, and LATPD can achieve that. And then you can start seeing the separation between Cherenkov light and scintillation. So Cherenkov starts immediately, and scintillation light is delayed. More than that, because of this spectral difference, if you use more red-sensitive photocathode, then this difference becomes even larger. So you're getting more and more separation between Cherenkov and scintillation light. And for our initial studies, we placed a cut of 34 nanosecond. Basically, we discard all light which is coming after 34 nanosecond. We use only early light, and this early light is enhanced in terms of Cherenkov light. And this is a distribution of angle of the photons with respect to the drag. If there were no time cut in this case, it would be a flat distribution because scintillation light is isotropic and you would see no difference, no preferred direction in photons. But since we select events with abundance of Cherenkov light, we do see a spike around the Cherenkov angle. So our strategy is to use early light, and if one can get us red sensitive photocathode, that would be even better. Or if there is any other way to separate Cherenkov light and scintillation light, and I will show a few slides on that. So for our first test, we used very simple algorithm. Don't read what is on the top of this slide. I will explain how we reconstruct vertex. So you have event in your detector, and you need to find where it comes from, because this is the only way you can find the vertex and place the cut on the early line. Otherwise, if you don't know where the vertex is, you will never know what time cut to place on the event selection. So reconstruction algorithm is very simple. We use any 4 numbers of photons and solve this type of equation. In ideal world, it's enough having just 4 hits and reconstruct the vertex in the assumption that the track length is very small. For this reconstruction, we assume that all light is emitted from a single point, which is a fair approximation, because the detector size is about 6.5 meters in our case, and the track length is just 3 centimeters. So our resolution would be intrinsically limited by 3 centimeter track length. But in order to deal with all real-world effect, we select a number of ensembles of these 4 randomly selected hits, solve this equation, and for each solution, we plot a time residual distribution basically for now using all photons altogether, and given our assumption of the vertex, we calculate what is the difference between expected time of arrival and really measured time of arrival of the photons. And the better solution is the more narrow distribution of this delta T will be. And we just select the one solution out of 400 which has most narrow delta T distribution. This is
the electrons as they come out, they're not going to travel in straight line. So the direction is the scatter.
Right.
It will be all smeared.
Right.
So
And this is taken into account in our simulation. So I will show results on in the next couple slides. So we use real simulation with all scattering effects taken into account. So for direction reconstruction, we use very simple algorithm. So in this case, we select only light which comes early, which is mostly Cherenkov light, and we just do synchronizing of all vectors pointing from the vertex. This is very simple. This will not work for 2 tracks, but we are not worried about that because there are plenty of algorithms looking for rings in the spherical detector. So this is a technical problem. It was more important for us to find out whether in principle we can reconstruct directionality of electron in a media which has huge amount of scintillation light. And here are some results of reconstruction. First, the vertex reconstruction shown on this plot. Red, blue, and black are different components of XYZ vector. Our electrons are simulated along the x-axis, and because our track length has about 3 centimeter extension, it is shifted, but it is shifted more than by 3 centimeters because in this equation we use single speed of light for every photon. But photons travel with different speed of light, and it does produce bias if you do not correct for that. So ideal approach would be to use likelihood and correct for each photon what is the best speed of light or wavelengths correspond to this photon. And for our future work, we will remove this shift by 6 centimeters, and it will become much less. So it will not be smaller than 3 centimeters because the track length is 3 centimeters, but 6 centimeters at the moment is related to the fact that we use single speed of light for every photon. On the direction reconstruction, this is the ratio of moment component divided by the total moment. Basically, this is a cosine of the angle between reconstructed track and true track. And with 5 electrons, this is very exciting and promising. This does include all scattering in Kamlets insulator. And the natural question is, what is low energies? How about low energies? We picked two energy points of half energy of cadmium decay and half energy of calcium decay. And first thing to look at is how many photons will you get in the case of energies which are relevant for neutrino-less double beta decay. So the circles are Cherenkov photons, very few, but they're still there. Squares are scintillation light, and blue is the ratio between Cherenkov and scintillation light. So with high energy, you're of course doing very good. At low energies, you're getting more scintillation than Cherenkov light, but still, this is after we've taken into account the quantum efficiency of typical Kalman photodiodes. So there is some Cherenkov light there, and the natural thing to do was to try this reconstruction algorithm on lower energies. And we did, and results are shown here. So we took the smallest energy. We're doing about the same on the vertex reconstruction. So the vertex constraint is in 4-6 centimeters, and depending on the direction. And the directionality information is still there. So we still can select events where electron goes into one direction. And this is very encouraging for us to continue and try to change algorithm so we can look for two tracks and try to find two tracks in the opposite hemispheres. This plot here shows how the cosine of this angle between reconstructed and true track depends on the energy. So obviously we are doing much better at high energies and at energies relevant to neutrino-less double beta decay. We are still doing okay. And this is with very, very simple algorithm. No significant amount of coding or thoughts how to improve it. So
In your, one more question that would be relevant to dark matter would be that your low energies, your scattering is more. So for example, you can't take this and make a directional drift because those are KEV.
yeah,
So
right.
they would just lose all direction.
Right, yeah, absolutely. With low energy or high dense materials like xenon, you will get a lot of scattering.
No, I mean even drift gas systems. You just can't use this.
Right. So, the time remaining, I have just a few slides to show where do we go from there. Typical isotopes considered in double beta decay searches are listed here. And just by coincidence, these isotopes are used in what is called quantum dots. Quantum dots are nanocrystals which has very unique properties. So the optical properties are determined by their size. And there is a whole engineering on how to make better insulators with quantum dots doping. So you dissolve quantum dots in this insulator, and this way you control the scattering, the absorption length, and the scintillation spectrum. And there is a very strong group at UCLA working on this problem, and they found out that just by accident, most materials used in quantum dots are the same as used in the searches for neutrino-less double beta decay. So the advantage of quantum dots doping is that it gives you controlled scintillation spectrum, and it can shift the scintillation spectrum to the lower wavelengths, to shorter wavelengths, and this way to increase the separation between Cherenkov and scintillation light. The strategy here is to dope scintillators with materials which undergo neutrino-less double beta decay. So I really recommend this if you would like to hear more about this. Is a whole new topic for a separate seminar, but these people do very cool stuff. This is just an example of their work on quantum scintillators. This is what they've already done. So they can make a very nice narrow scintillation spectrum. And this is how it compares with broad Kamlett spectrum. And for our particular application, this spectrum sits on top of Cherenkov line. And we'd like to move the spectrum towards shorter wavelengths in order to increase separation between Cherenkov and scintillation line. This has not been done, but they are very positive that it's very possible in the near future. So, what our strategy for this? How do we continue? We have a pending proposal to demonstrate that what we have done in simulation and reconstruction is actually can be done in a real experimental setup. So we plan to use 1 meter tank filled with liquid scintillator and just try to reconstruct electron direction using some sources and utilizing fast timing to separate Cherenkov line and scintillation line. Also, LEPPDs are imaging devices, and this has to be fully explored. One thought we have is that you can map the large volume using mirrors onto a very small number of photosensors. And this way, you can save a number of active elements in the detector, and this is probably the only way to keep budget under control. And also, work is in progress to build a modular design for kiloton scale detector. So you don't make a giant detector at once. You go with a stage approach. You build several models as time permits and as budget permits. And with every new model, you are getting better because you understand your system better. And I think this concludes my presentation. As a summary, I think I tried to convince you that many applications can benefit from precise timing and covering large area. With LEPPD detectors, we are approaching picosecond domain, not quite single picosecond yet, but tens of picoseconds seems to be very close. There is a company in Massachusetts which is very serious about making them commercially available, so in a few years one can buy them from income. And first adopters for LEPPD detectors are identified, and they are seriously considering what LEPPD detectors will do for them. And what I find particularly interesting is that experiments looking for neutrino-less double beta decay can use this technology to look at Cherenkov light. This has never been done before. No one ever looked at Cherenkov light in the top of scintillation line. People were talking about it in the giant detectors where you have huge energies absorbed of GV, and people were talking about separating Cherenkov light and scintillation light. But for something like neutrino-less double beta decay, it has been thought about. There is a lot of work to be done, but I truly believe that it is possible, and the sensitivity of these experiments can be vastly improved. I think I conclude here. Thank you very much.
Yeah, thanks, Andrey. Please, Dave.
So, what devices are the Berkeley guys making that they're interested in?
They make exactly the same tiles that are 8 by 8 inch, same geometry. Let me show you that on the first slide.
But what are they using them for?
They will send them to space and do imaging. They do it for imaging. They are not so interested in fast timing, but rather in microcapillary structure, which gives you very fine spatial resolution.
It's really an astronomy.
Yes, this is for astronomy. And the only difference between us and them is that they are using ceramic body.
Oh, so what they probably like is for it to be cheap and light. Actually, probably light.
Well, let me tell you this. One model from Berkeley would cost $1 million, and the other one would cost $1 million, and the third one would cost $1 million. So ceramic is very expensive.
No, but I mean, to put it up in space is $500 million.
Right, yes. But particle physics community will never afford it. I mean, single phototubes for $1 million is impossible. The last, on the contrary, is very cheap. And this is going to be a few K in terms of pricing. Yeah, so their budget is for space missions are much larger.
Andrey, can I ask, you had this, Maria apparently was buying these modules, right? So is she doing this for colorimeter? Maria Spiropoulos is
Maria, yeah.
planning to buy this. So she's thinking about doing the pile-up separation of
Yes,
forward colorimetry.
they're talking about.
And what kind of
colorimetry.
rate can these devices take?
This is a question we always getting. The answer is that we don't know, but one thing we know is that they are very robust in terms of charge drawing. So you can draw a charge up to 10 coulomb without any degradation.
Yes, I saw that plot.
Yeah, and in terms of how much rate, you have to stick into the test beam and see what it is. So I'm not allowed to quote any numbers.
Because if she wants to put it in HCAL, you know, she'll have to deal with that.
Yes, they are very much aware of this problem, that the rate is very high and we have to deal with very high rate.
Other questions? If not, let's thank our speaker again.